Welcome to This Explainer. Today we're unpacking the absolutely fascinating toolkit that ecologists use to make sense of our massive, complex natural world. I mean, have you ever really thought about how scientists actually know what's going on across an entire rainforest or a sprawling coral reef? It's not like they have magical scanners, right? And there's definitely no time to count every single leaf or critter. Instead, they rely on a pretty incredible combination of clever field tools and hardcore mathematical design. So let's dive right in. The core problem is that it's literally impossible to count every single leaf, track every roaming predator, or catalog every bug in a forest. These ecosystems are just too huge, too dense, and way too dynamic. So how on earth do researchers gather accurate data without spending 100 years stuck in the woods? Well, the answer lies in the highly calculated art and science of sampling. Which brings us to our roadmap for today. We're going to cover the power of sampling, designing the perfect study, field tools and traps, probability sampling methods, non-probability sampling methods, and finally, avoiding common sampling errors. All right, kicking things off with Section 1, the power of sampling. Let's build our foundation by looking at what exactly gives this process its power. So at its core, sampling is kind of the ultimate ecological workaround. When a researcher needs quantitative data to monitor environmental changes or track where certain species are hanging out, they've got to decide exactly who and what to measure. By selecting a carefully managed, smaller group, they can actually get a highly accurate reflection of a massive population that would otherwise be completely unmeasurable. And honestly, the design of this process is everything. Think of representativeness like tasting a spoonful of soup. If that soup is well stirred, that single spoonful tells you exactly how the whole pot tastes. Proper design ensures our data isn't biased towards just one weird corner of the ecosystem. Plus, it brings immense efficiency, saving a ton of time and money. But most importantly, it gives us statistical validity, which is that rock-solid foundation we absolutely need to draw real, reliable conclusions about the environment. Moving right along to Section 2, designing the perfect study. Because before an ecologist ever steps foot in the wild, they've got to do some serious planning at their desk. During this planning phase, it's all about a balancing act. First off, what are your clear study objectives? What are you actually trying to find out? Second, you have to consider population variability, meaning just how diverse and unpredictable is the landscape you're looking at. And then you have to weigh those lofty scientific goals against gritty real-world constraints, things like your budget, your timeline, and making sure your sample size is actually big enough to give you real statistical power. Those design factors then translate directly into standardized step-by-step field procedures. Once the master plan is set, you absolutely need consistent methods to ensure your data is reliable. This all starts with picking truly representative sites, meticulously recording every single observation, and properly preserving any specimens. And finally, there's the chain of custody. Researchers have to track the handling of those samples perfectly, every step of the way, from the muddy forest floor all the way back to the pristine laboratory. Okay, Section 3, field tools and traps. With our plan in hand, it's finally time to crack open the physical toolkit and look at how we actually survey flora and fauna. Now, what's really fascinating here is the stark contrast in how we study different types of life. When we're dealing with flora, plants and stationary organisms, ecologists use things like quadrats, which are basically defined squares used to sample abundance, or transects, which are essentially straight lines drawn across a landscape to study how things change along a gradient. But when looking at mobile animals, totally different ballgame. We use active tools like glowing light traps deployed in the dead of night to capture nocturnal flying insects. And the toolkit gets even more specialized than that. For really elusive or highly mobile species, ecologists might deploy chemical traps or pheromones, kind of like the suspended trap you're seeing right here. Instead of just crossing their fingers and hoping a bug flies by, these traps emit very specific scents. It's a targeted approach that actively draws specific organisms right out of the dense brush and into the sample. So, we've got our specimens, but how did we decide exactly where to place those traps in the first place? That brings us to Section 4, probability sampling methods. This is where we hit the big divide in the ecological toolkit. On one hand, we have probability sampling. This is highly objective, kind of like rolling a perfect mathematical die, because the chance of selecting any single unit in the population is actually known. On the completely opposite hand, we have non-probability sampling. Here, the chance of a unit being selected is totally unknown, which makes the whole process highly subjective. Let's focus strictly on those mathematically sound probability methods first. Because every single unit has a known, objective chance of being chosen, these methods are basically the gold standard for minimizing our own human bias. There are 4 main types that ecologists rely on. Here's how they break down. If a forest is nicely uniform, we can just use random sampling, where every single spot has an equal chance of getting picked. Or we can use systematic sampling, setting up traps at regular, predictable intervals. But let's be real, nature is rarely uniform. If the landscape is super diverse, say, shifting from deep, shady valleys to rocky peaks, we use stratified sampling. This divides the area into subgroups to ensure every unique microenvironment is fairly represented. And finally, if we're dealing with a massively large area, we use cluster sampling, where we select entire representative groups of units to study all at once. But what happens when random selection just isn't practically possible? Welcome to Section 5, Non-Probability Sampling Methods. Sometimes a terrain is just too dangerous, or a species is entirely hidden. We have to shift to non-probability methods, but man, we have to do it with extreme caution. The most basic, and frankly the riskiest, is convenience sampling. This relies entirely on what's easy to access. It's literally like testing the soil right next to the parking lot, just because it's a short walk. The disadvantage here is pretty glaring. You leave with absolutely no idea if your sample actually represents the deep, unreachable parts of the forest. To inject a bit more rigor into the process without true randomness, researchers use more targeted methods. For example, there's judgment sampling. This is where an ecologist uses their specific, hard-earned expertise to deliberately select populations that are rare or tough to find. It's unashamedly subjective. Then there's quota sampling. This method sets predetermined quotas to mathematically force the sample to match known traits of the broader population, even if the individual selections weren't truly random. And for populations that are just incredibly hard to track down, researchers use a fascinating technique called snowball sampling. Just like it sounds, it builds momentum. It's a sociometric technique where the first few subjects you identify actually lead you to other similar subjects. While you see this a lot in the social sciences, variations of it are absolutely critical in ecology too, like when one rare discovery in the wild points investigators down a trail to uncover a completely hidden ecological network. Now, even with the absolute perfect statistical method and the highest tech traps money can buy, things can still go incredibly wrong. That brings us to Section 6, avoiding common sampling errors. These pitfalls are known as non-sampling errors. And here's a kicker. They have absolutely nothing to do with the size of your sample. Instead, they are sneaky, hidden biases that creep in from other places. We're talking about human observation errors out in the field, wonky measurements from uncalibrated gear, or even just simple, devastating typos made back at the desk during data processing. You could even be dealing with defective frame coverage, which is really just a fancy way of saying the map you used to plan your entire study was totally out of date before you even started. Understanding an entire ecosystem is a truly monumental task. But, as you've seen, through careful design, precision tools, and a hyper-awareness of our own biases, it's actually possible. So, armed with this new knowledge of transacts, probability clusters, and chemical traps, I want to leave you with a thought to chew on. How would you apply these exact tools to uncover the hidden ecological story of your own neighborhood park? It's like a giant puzzle right outside your door. Thanks so much for joining me on this explainer, and keep exploring out there.